And with that, the empire was unified.
What if the speed of light is always constant?
Well, you're wasting my torch. Leave the class now!
Instead of answering, his teacher rejected him. The boy's name was Albert Herman Einstein. Einstein walked out of the classroom that day, but the question never left his mind. It stayed with him, growing stronger day after day, because sometimes the questions we're told to ignore are the ones that change everything. The question was, what would the world look like if you could run at the speed of light?
What would I see if I could catch a beam of light?
Now, it sounds like a childish question, right? But what if you could run at the speed of light? This simple thought was about to shake the very foundation. From a simple, curious question emerged the most groundbreaking theory in physics, a theory that would forever change how we understand space, time, and the universe. Einstein took a simple, curious question, what would the world look like if I could ride a beam of light? And turned it into a powerful thought experiment. For over 200 years, Newton's laws were the word of God, absolute, predictable, and unchanging. But Einstein saw the cracks. Gravity is not instant, and time is not the same for everyone, into a revolution. Groundbreaking theories, ideas so radical they seem impossible. How could anyone think of them? By asking simple questions and daring to challenge the obvious, he unlocked truths hidden to everyone else. And can I also think like that? Can I see the world differently? Imagine what others cannot? And ask the questions that change everything? The answer is yes. Now, friends, many people think that Einstein's theory of relativity was just created based on Newton's theory of gravity. Let me tell you, you guys are absolutely wrong. Because Einstein's relativity wasn't directly derived from Newton's gravity. In fact, it was invented from two of Newton's other theories, which surprisingly have no connection to gravity in the slightest. In fact, at that time, Newton had already introduced three fundamental theories to the world: the laws of motion, the concept of inertia, and the idea of forces acting at a bit of distance. The second theory, the particle theory, according to which light travels from one place to another in the form of tiny particles, or corpuscles. And the third, relativity. Yes, Newton also introduced a theory of relativity. According to him, the laws of motion are the same for all observers moving on Einstein's relativity. If two cars are moving in the same direction at the same speed, and from your perspective, you stop them in your frame of reference, they will appear to be close to each other. Motion is relative. But if two cars travel in opposite directions, face to face, then their speed, as seen from one car, will appear to be double. In short, speed and motion are always relative. In other words, the speed of every moving thing depends on your own speed. Motion is always relative, depending on the observer. Now you can see, these three theories are quite different from each other. One explains gravity, another explains light, and the third explains motion. Each theory had its own domain, its own rules, yet none of them alone could explain the universe the way Einstein would. At first sight, these three theories seem completely unrelated. Gravity, light, motion, nothing seems to connect. But you know what's the weird part?
Giving birth to Einstein's theory of relativity. What seemed disconnected, indistinguishable, became the foundation of a revolutionary understanding of the universe.
Einstein Theory in 1629 much earlier. When Dutch physicist Christian Huygens, this challenge planted the seeds that would, centuries later, help Einstein see the hidden connections.
According to Newton, light travels in the form of small packets of energy called corpuscles.
But according to Huygens, light bends when it passes from one medium to another. And that's why he argued it must travel in the form of waves, not particles. But because Huygens didn't have experimental evidence to prove his theory at that time, no one accepted his wave theory of light for the next 100 years. Newton's particle theory remained dominant. Until 1801, when British physicist Thomas Young finally proved Huygens' idea. Through his famous double-slit experiment, he showed that light doesn't behave like particles, but like waves. Young passed light through two tiny slits and observed the result on a screen. Now, if light were just particles, you would expect to see only two bright spots. The two beams, he saw something interference pattern.
For the first time, Young's experiment proved Newton's theory wrong and showed that light is not just particles, but a wave, a truth hidden for more than a century.
But wait, let's pause for a moment. We all know every wave needs a medium to travel. Water waves need water, but in outer space, so how does light travel through empty space? This question troubled scientists for years. If light is a wave,
then what is it traveling through? To answer this, some scientists proposed a bold idea that space is, but as I said, this was only a hypothesis. It had never been proven experimentally. And that's why, in 1880s, Albert Michelson and Edward Morley, their experiment was designed to detect this effect. People inspected taking one of the most famous failed experiments in history. No matter how they measured, no matter how they adjusted the setup, they found absolutely nothing. No sign of ether at all. Look, Michelson and Morley's idea was actually very simple. According to them, if ether exists and it is flowing in one direction, then when light travels in the same direction as this ether flow, it should be pushed forward and its speed should increase. And at the same time, when light travels in the opposite direction of the ether, its speed should decrease because now it is moving against the resistance of the medium, just like trying to run against the wind. Simply speaking, Michelson and Morley believed that if the speed of light changes, then the existence of ether would automatically be proven, because any change in speed would
But in front of them, the biggest question was, how could they detect the invisible ether and prove that light's speed changes as it moves through it?
Then they realized, in Young's famous double-slit experiment, both light waves created an interference pattern because they were coming from the same direction and moving at the same speed. Now, here's the crucial point. If two light waves were traveling at different speeds, one with the ether, one against it, then when they collide and combine, the bright and dark bands would no longer line up perfectly. To test their assumption, Michelson and Morley sent the light waves in two opposite directions. They reflected the beams off mirrors so that the two waves would meet again at the same point, forming an interference pattern. But when they actually performed the experiment, once again, they were extremely disappointed. The interference pattern remained perfectly intact. The ether, the invisible medium that was supposed to carry light, simply did not exist.
Pattern, no matter the direction of the light beams. And this led to two extremely important carrying light does not exist. Second, the speed of light is constant, no matter the motion of the source or observer.
And the results proved two groundbreaking facts. First, there is no medium like the luminous feed in all directions, regardless of the motion of the source or the observer. As and tested for decades, was disproven forever. Light doesn't need a medium to travel, and the universe had just revealed one of its most mysterious truths. But as soon as Michelson and Morley proved that the speed of light is constant, Newton's second lesser-known theory, relativity, made a comeback. Two cars moving in the same direction appear stationary relative to each other. And because of this, the challenge of constant light speed, the failure of ether, and the hints in Newton's forgotten theory of relativity, Einstein realized that he would explain the universe a completely new theory ever imagined before. So in 1905, Einstein has had a thought. According to Newton, speed is relative. Two objects moving in relation to each other experience motion differently depending on their frames of reference. But then, what about light? It means the speed at which I am traveling, if someone comes in front of me at the same speed, then I will perceive his speed as double. Motion is always relative to your own speed and the speed of the other object. But just now, Michelson-Morley proved that the speed of light is constant, which means this was the paradox that classical physics couldn't explain, and it was exactly what Einstein had to solve.
Which means, then the wave ring, and just like that, a paradox is created. This is the puzzle that forced Einstein to rethink the very foundations of physics. So here's the question, who is right and who is wrong? Newton's idea that motion is relative, or the evidence from Michelson and Morley that the speed of light is constant? But who is right and who is wrong? Stay tuned for part 2 to find out. Part 2 is coming soon.